Hey, Castle here. Welcome to Memphis Communiversity. Today I'm going to be working through the differential equations review worksheet with you all. If you haven't already seen all the videos on the differential equation unit on this YouTube channel, go check those out and make sure that you watch those or that you understand these topics before we do the review, because it's going to combine all those things. A lot of this is geared towards AP exam questions, the last two questions being exam questions just for the BC Calc exam as of 2020. So just keep that in mind. And college students, this isn't going to include everything that you're probably learning in your classes, but a lot of it is really helpful. And these are more the basic forms of a lot of these different topics. So if you like this video, if you think it's helpful, watch the other YouTube videos on this channel. And just a reminder, this worksheet as well as the answers are in the description below if you want to print those out and work alongside me or just look at them later. So let's just get started. The first question that we have is a slope field problem. And so these slope field problems are exactly what they say. It's just a field of slopes. And these ones usually take a little bit of time, but they're not too tricky. It's just exactly what it's asking for, and the slope is already given if you see that dy over dx. So I'm just going to start by rewriting that given out on the side because I'm going to be doing some work there with that. And then if you look at those little points, the first thing that you want to do is what I'm doing here. You don't have to do this on every one, is I'm just labeling this point to make sure that I can easily match up my x's and y's and keep everything straight. So I'm going to work through the first few points slowly, starting with 0 over 0. And for these slope field problems, the main thing that you're doing is at each dot, you are taking that x and y and plugging it into the derivative. In this case, the derivative is given. Remember that the derivative is the slope, so you're just finding the slopes with that derivative. And as we go through these ones, I'll teach you some different tips about slope fields, so let's get started. So with that 0 over 0, I'm plugging it in, y being 0 and x being 0. And when I plug it into the derivative or slope, I'm going to get -1. And then once you get that derivative, you're just going to go down to where that point is and draw a little line with the slope. And since the lines can get a little confusing and I'm not an artist, I'm going to write m equals -1. Obviously, you don't have to do this on every single one, but if you're like me and you just want to make sure that you are keeping everything straight, then I think it's pretty helpful. So since I'm going to be doing work over here, I'm just going to move myself up to the corner and we'll get on to the next one. So this next little dot is 1, 0. So I'm going to plug that in. And I've got 0 minus 1 over 1 plus 1. That's going to be -1/2. And then I'm going to go over there and do my little slope. Notice that when I drew it, I made it a little less steep than the first one. Just remember that the bigger the slope, the steeper the line. So since my slope is less than -1, the line is going to be a little less steep. And then moving on to that last one, the point is 2, 0. So I'm going to plug those in. And after I do these three, I'm not going to be showing all the work for these because this is pretty easy. You can do it in your head. And I'm going to get -1/3. Again, a smaller slope, so a less steep line. Okay, so for this next line of points, I think it's helpful to notice that the y is the same for all of them. This is something that you might see sometimes, and it's pretty helpful because you're going to have a slope that looks the same for all of these. Because if you look at that y minus 1 on the top of the derivative, if you plug in 1 for every single one of those points, you're going to end up with a slope of 0. So you'll see this with horizontal lines, positive and negative. Make sure that, or you'll see that with horizontal lines where all of them are the same slope. Or if you have all negative, all positive, then you have to make sure that those slopes are all going the same direction. So just being able to recognize patterns in this is going to make it take a lot less time and help you not get confused with all the different numbers. So like you can see on that bottom line, they're all negative, so they're all going in that direction. And then on the second line, the slope is 0 on all of them, so obviously they all look the same. And then on this third one, they are all positive, so they're all going in that direction. And they're pretty much the same slopes as the bottom line. So I didn't really show a lot of work for those because it's pretty similar to what we did on the right side here. So that is your slope field, and you're just drawing all of those slopes and making sure you are careful with positives, negatives, making sure that you don't get your numbers confused as you're working through. Okay, this next problem is not too bad. It's probably something that you've seen some form of before. It's a tangent line, and then here it's a tangent line approximation. So that means we're going to just do our regular tangent line work, and then there's going to be one extra step at the end. So let's just start with the tangent line. A tangent line, remember, is the using the point and slope formula where the slope is the derivative. So we have a point and we have our slope, the derivative. So it's pretty easy for us to figure out what all of that is. I'm going to write the given point and derivative over on the side here. And then I'm just going to start plugging in that point for the derivative. So there's my derivative, my slope. And then I'm going to plug in the point to get the slope. And then once I get it, I'm just writing the tangent line using point slope form. So I'm going to have, let's see, y minus 1 equals, and then I have that slope that I found by plugging in the point 7 times x minus 4. Okay, and then the next step here is to approximate. So we're given f of 4.2, the 4.2 being in the place where an x usually is. So that just means we're going to plug in 4.2 where our x is on the line that we made. And then we're going to just solve that like we would solve anything else, isolating the y. So you would have y equals, and then I did some work in my head, 1.4, and then adding the 1 at the end is going to give you y equals 2.4. So the only extra step on that one is after you find the tangent line and write it out, you are just going to place that x or whatever value is given into the point slope formula that you made, and then just go ahead and solve. So this has a differential equation, but overall it's really just a question about concavity. So the question is RT concave up or down when r equals -2? And I just want to remind you that a function is concave up when the second derivative is greater than 0, and it's concave down when the second derivative is less than 0 or negative. So on this one, it's basically just trying to find the second derivative, but something I want to point out is that dr over dt is pretty much just like a dy over dx, which is what you usually see. And why that's important is because if you look at the function, it's 30 minus 3r, and since the r is in the place where a y would usually be, remember that if you had a y in a function, you always have to do implicit differentiation. And that's the same with any letter that you're going to see, whether it's r or w, whatever it is, you have to do implicit differentiation. So I was just going to point that out before we start working, and you'll see where that comes into play as we work through this problem. So the first thing that I'm going to do is I am just writing that second derivative, and then here I'm going to write -3r prime. So notice, like I said, if that r had been an x, then yes, the second derivative would have just been -3. But because it's an r, the same way that you have to do implicit differentiation for y when you see it, you also have to do it for this r. So I have -3r prime, and I'm just going to rewrite that. Sorry about that. I'm just going to rewrite that as -3 dr over dt, because then you'll notice that that dr over dt is the same that's written in the given. So the best thing to do here is just to go ahead and substitute that given since it matches up the dr over dt. So then you're going to have -3 times 30 minus 3r. And from there, it's just a matter of plugging in the givens. So you would have -90 plus 9r, and then you see in the problem that r equals 2. So you plug that in, you have -90 plus 18. And then remember the question is about concavity. So you've got -72, and -72, remember, is the second derivative. So since -72 is below 0, you're going to have concave down. So I'm just writing out the justification for that. It's concave down because the second derivative is less than 0. And there's your answer. Okay, these next few problems are just some basic separate and integrate problems. Remember that if you're confused on any of these, there is a separate video for separate and integrate. So go ahead and watch that and then come back here if these are confusing to you. So here we're given a differential equation and it's asking us to find a particular solution to that differential equation. So the first step that we have to do is separate. So what I'm doing is basically cross-multiplying, and I'm going to separate it like that. You can see I have integral 2w dw equals integral 3t squared dt. So I've just cross-multiplied and written it. I haven't integrated yet. And integrating is the next step. So these are pretty basic integrals. I'm going to have, let's see, w squared. That integral I would find by looking at that implied 1, that is w's exponent, adding 1, and then flipping that, but it's still going to be 1. And then I am going to have w squared because 1 plus 1 is 2. And then that is going to equal that integral of the next one. You do it the same way and you're going to get t cubed. And the most important thing here is to have plus c. The plus c is really important. Every time you do separate and integrate, you have to have that. On the AP exam, you'll get a whole point just for having that plus c written. So make sure that you have that. I'm going to triple underline it every time I see it. And so the next step here is to figure out what the c is. So I'm going to take that point that was given to me, and I always just rewrite the point to make sure I don't get any numbers confused, because this step shouldn't be too bad as long as you plug in x and y where they're supposed to go. So here our x and y are actually t and w. So I'm going to get 16 equals negative 1 plus c when I plug in those points. And I'm going to get c equals 17. So then I'm just going to rewrite what I had before, that w squared equals t cubed plus c, but we know c is 17 now. And then the final step for these separate and integrate is to isolate the variable, since we are finding a solution. So the way I'm going to do it here is taking the square root of each side so that we can isolate w. So technically the square root of w is plus or minus square root t cubed plus 17. But remember that we have to have one solution, so we can't have plus and minus. So the way that you figure out whether it's plus or minus is you plug in those numbers that you were given and see which one actually gives you the right solution. So if you plug in negative 1 for t with the one that you're given, you should get negative 4. And you only get negative 4 on the negative function. So I'm going to rewrite the answer, taking away that positive sign, so that I have w equals negative root t3 plus 17. So that square root kind of makes it a little bit tricky. That's a pretty rare way that they're going to ask the problem, but just watch out for those and make sure that you only have one solution. Okay, this is just another basic separate and integrate problem for practice. So let's get started. So on this one, I'm finding the solution to this differential equation. And the first thing that I want to do is the separate step. So I'm going to have, when I cross multiply, I'll have the integral of dy over y plus 2 squared equals the integral of 2 sine x. And this is just a good time to bring up the fact that when you have a coefficient in a function, I like to put it on the x side because that's just going to make things easier as you're solving it. So that 2 is a coefficient, and I'm just going to keep it on the x side. And then remember that when you're cross multiplying, sometimes I'll write a line below that whole function and say over 1, so that when I'm cross multiplying I can kind of just see what I'm doing, because remember that the 2 sine x is across from that dx, but the y plus 2 squared is right next to the dy, so you have to put that over 1. That's why I have dy over y plus 2 squared, but I don't have a fraction in the second one where I just have 2 sine x dx. So let's go on and do the integrate step. And something that I want to point out here is not every integral is going to be, or not every time that you have dy over something is it going to be ln. In this case, it's just, I rewrote it as integral y plus 2 to the negative 2. Because you have that exponent of 2, you're not going to have ln. It just turns into a regular integral, and it is going to be, let's see, negative 1 over y plus 2. And then the next integral is a pretty basic one. Remember that the integral of sine is negative cosine, so you have negative 2 cosine x, and that plus c is huge. So the next step is always going to be to find the c. So in this case, we have to plug in our given point, 0, 3, and that's going to give us negative 1/5 when we plug in that 3 for y, equals negative 2 plus c. So if we solve for c, c is going to be 9/5. Okay, so then we're going to take that 9/5 and just rewrite what we had, subbing in the 9/5 for c. So you're pretty much just rewriting things. Negative 1 over y plus 2 equals negative 2 cosine x plus 9/5. And the next step here is to isolate y. So the first thing that I'm going to do is just multiply all of that x side by the negative to get rid of the negative on the y side. So I'm going to do 1 over y plus 2 equals 2 cosine x minus 9/5. And then the next thing I'm going to do is I'm going to just combine these last two steps into one. To get rid of the fraction, I'm going to put all of the x side over a 1 so that I have the y by itself. 1 over 2 cosine x minus 9/5, and then I just subtracted the 2 at the very end to have that y isolated. So that's your solution to the differential equation. I'm just going to box that. It kind of got messy under there, and there's your answer. Okay, this next one is, oh, hello. This next one is a little bit more of a complicated one, so just bear with me. And again, I highly encourage you to watch that separate and integrate video in the differential equations unit if you are not understanding all of this completely. So we are finding the solution to this differential equation. Of course, the first step to any of these is going to be to separate. You do your cross multiplication and you get integral for secant squared x d of x equals integral 1 over 2y plus 1. And remember, on that previous problem, you had a fraction, and I think it was y plus 2, but it was squared, so you didn't have ln. But in this case, you are going to have ln when you integrate. So I put my x first and my y second, but as I integrate, I'm just going to flip those to make my work a little bit easier and a little less messy. So I'm doing that y side first. And what I did here, I didn't show it all, was a u sub. And so on this u sub, my u was that 2y plus 1, and my du was a 2, which is why I have a 1/2 before the ln, because I multiplied by that integral. And so I have 1 ln absolute value 2y plus 1, because when I integrated that u sub, I got an ln, and then I just substituted back in that 2y plus 1. So I'm just going to keep working here. I've got 1/2 ln absolute value 2y plus 1 equals 4 tan x plus c. Remember the plus c always, because that's always going to be our next step. So here, since we have an ln, what we're going to do is something called the a way. And I'm going to show a lot of steps for it, but at the end I'll show you where you can just kind of skip from one place to the next. I just want to show as much work as I possibly can. So the first thing that I'm going to do here is just divide everything on that x side by the 1/2 to make things a little bit simpler. Oh. Sorry about that, I'm back. So like I said, we are going to be dividing that whole x side by 1/2, which is the same as multiplying it by 2. And we're doing that just to make things as simple as possible and get that ln of 2y plus 1 on its own. So when we multiply by 2, we're going to get 8 tan x plus c. And technically you can do a 2c because you're multiplying everything by 2, but we're going to change that c later, so it doesn't really matter what it looks like now. And the next thing that we need to do is get rid of that ln. So the way that you need to get rid of an ln is you raise e to the power of both sides. So when you raise ln of 2y plus 1, when you raise e to that ln and the e are going to cancel each other out, so you're left with 2y plus 1. And then when you do it on the other side, you're going to have e to the 8 tan x plus c. And there's an exponent rule that tells us that when you have an exponent that has addition in it, you can actually split it into two different exponents that are multiplied by each other. So that's what we're going to do here. We're going to take that e to the 8 tan x plus c and write it out as e to the 8 tan x times e to the c. Okay, so now you've got that 2y plus 1 equals e to the 8 tan x times e to the c. And since we have that e to the c, it looks like a really complicated thing, and this is called the a way because when you get to this point that you have e to the c, you're actually just going to change it to an a. We're just going to call all of that a. So let's see. Okay, I'm going to rewrite this as 2y plus 1 equals e to the 8 tan x times a. That e to the c has just turned into an a. And then just to make things simpler and a little more readable, I'm going to rewrite that as a e to the 8 tan x. Okay, so now that you have that, the next thing that we're going to do is figure out what a is. So c isn't really important now. The c was the exponent of that e, and we changed it all to a. So now that we have the a, we can just kind of forget about the c, and a is going to be kind of like our c. It's going to be the number that we're trying to find when we plug in the points. So I'm just going to start doing that. Our given point is 0, 2. So thinking about that equation that we had, 2y plus 1, that's going to end up being 5. And then you set that equal to a to the e 8 tan x. Our x here is 0. Remember that e to the 0 is 1. So what you really have is 5 equals a. So now that we have our a, I am just going to rewrite. Sorry, I'm going to have to move everything over here. It's getting a little messy. I'm just going to rewrite that as 2y plus 1 equals 5 e to the 8 tan x. So now it's just like any other separate and integrate problem where you want to isolate y. And the way we're going to do that is pretty simple. We're just going to divide everything by 2 and then subtract a 1 at the end. So we've got that y by itself. So like I said, I showed you a lot of steps here, and really you don't have to do all those steps. Once you get the hang of these problems, you can kind of skip from, I'll give you an arrow here to show you, you can kind of skip from that step where you have the plus c and go all the way to the step where you have a, e to the whatever it is that you have, and then work from there trying to find the a with the given points. So again, review the separate and integrate video if you need to, and the more you do practice on those A-way problems, the easier they'll get. Okay, the next thing we're doing is an Euler's Method problem. Euler's Method is kind of a long thing to memorize, but once you've memorized it, the problems themselves aren't too bad. It's just kind of keeping track of your numbers and all of that. So Euler's Method says that the new y, and we'll kind of go through what all of these are as we do the problem, equals the previous y plus the step size times the slope or the derivative using the previous x and y. So that all sounds kind of weird, but it makes sense once you start seeing all the numbers together. So the easiest way to do these, I think, is to write out little columns for your x and y. I think it helps just keep track of everything as you work through the Euler's Method problem. So I'm going to make my x and y column, and I'm just going to start with the given. You're always going to be given a point at the beginning. So I've got 1 and 4. And remember that the question is asking to approximate f of 0 with 2 equal step sizes. So we're going to have 2 different numbers, and the last one is going to be f equals 0. So if you have 2 equal step sizes, then you've got to go from 1 to 0.5 to 0. And so the thing to pay attention to here is that you're going from a bigger number to a smaller number. So your step sizes are going to be negative. And remember, step size is part of that equation. So it's really important to know whether you're working with a positive or negative one. So we're just kind of going to go through the equation for our second number. So we've got our previous y, that one's 4. You can see it up at the top of the column, plus our step size, so plus negative 0.5, and I'm just going to write minus 0.5, times the slope or the derivative using our previous x and y. So you can see that that derivative is given in the problem, and so I'm just going to take my previous x and y, 1 and 4, and plug it into the derivative that's given. So you've got that 2x plus y there, and then I've got 2x being 1 plus y being 4 right there, and simplify that to 4 minus 0.5 times 6, and that equals 1. But we're not done yet because we can't stop until we have the 0 right here. So we're just going to use the same equation using this 0 as our x, and then using this 0.5 and this 1 as our previous y and x. Once you get to the next step, you can kind of forget about those things earlier because you're only working with the previous x and y, not the original x and y. So we're just going to follow the equation here. Our new y is going to equal our old y, or our previous y being 1, minus 0.5, that's our step size, and then remember to plug in 0.5 and 1 into the derivative, and you're going to get 1 minus 1 equals 0. Hey, so my webcam turned green and purple. Not sure why, not sure how to fix it, so I'm just going to leave it because we only have one question left. So this is another BC question. 7 was a BC question too, both as of 2020. So an AB student wouldn't see this on the AP exam. But this is a logistic differential equation. And whenever I see a logistic equation, the first thing I do is I just go ahead and draw the graph of that because it helps me visualize as I do the problems. So a logistic equation has kind of an S-curve to it. So when I draw it, I'm going to do that S-curve. And then what I'm doing now is I'm drawing this dotted line, and the dotted line represents the carrying capacity of the logistic equation. And that carrying capacity in this question is the population size that the population will eventually approach in time as it moves toward infinity. So that carrying capacity is an asymptote, and the logistic equation is kind of moving towards that asymptote or that population size. And then the thing I'm drawing now, that point is the inflection point. You can see it's an inflection point because you have this concave up that switches to a concave down, and the inflection point here is half the carrying capacity. You can see that it is right at the halfway point of that S-curve, and this inflection point is where the slope of the logistic equation is the steepest. You can see that there. Saying that the slope is the steepest is basically the same thing in this problem as saying the population is growing the fastest. So that'll come into play later, and I'll point that out when we get there. But this first question here is asking about, I'm just writing inflection point there. So as I write that, I'm just going to explain what this first question is asking for. Like I said, the carrying capacity is the population size that the population will approach as time moves toward infinity. So that limit t to infinity is expressing that idea. So that first question is asking for the carrying capacity. And the way you find carrying capacity is pretty easy. You look at that logistic equation that's given, and you just take whatever's in the parentheses and set it equal to 0. So in this case, what's in the parentheses is 2 minus p over 600. So I'm going to write that out, set it equal to 0, and I'm just going to start solving that. So when I solve, what I'm going to get is p equals, and then I've got 1200. So then I'm just rewriting it as limit t to infinity, and that is 1200. Okay, so this next question is where that inflection point comes into play, because it's asking where the dp over dt, being the derivative or the slope, where that is a maximum. And like I said, you can see that the slope is the steepest at that point, that inflection point, halfway along the S-curve, that logistic growth, or that logistic differential equation. So the steepest slope means that that's where the population is growing fastest, and that's where the derivative is the maximum. Those are all kind of saying the same thing. And so to find that maximum derivative, the first thing that we need to do is just figure out that inflection point, and that's pretty simple. All you do is take the carrying capacity and divide it by 2. We already know that the carrying capacity is 1200, so when we divide it by 2, I was just writing the steepest slope is when you have carrying capacity divided by 2. So that's 1200 divided by 2, and that's going to be 600. But we're not done yet because we have to find the actual slope of the population when the derivative is at a maximum. So we know that the t is 600 when the derivative is at the maximum. So I'm just going to plug 600 into the derivative, which is given. And so I'm going to get 1/4, 600 times 1 equals 150. So the first thing I did was I found where the derivative was a maximum. That would be the inflection point. That's halfway along that S-curve. So I did 1200 divided by 2 is 600. And I plugged in the 600 to the derivative to get 150. And this last question is kind of just a question about concavity. So what I did here, and I would do this on any problem that I see about concavity, is I kind of label the things that it's asking me for. So the first thing it says is the derivative is greater than 0. So I know that that means that it would have to be increasing, because wherever f prime is greater than 0, it's increasing. And then the second thing it asks is where the second derivative is less than 0, which is the same thing as saying concave down. So I'm looking for a place on that graph that is both increasing and concave down at the same time. So I'm just going to redraw the graph here, just so that you can see it very clearly next to the problem. And I already know that that inflection point is 600. I found that in part 2. And I know that that carrying capacity is 1200. I found that in part 1. So you can see on that graph that the only place it's increasing and concave down are from 600 to 1200. Okay, so now that I've got those numbers, I am just going to start writing that out as a sentence, the kind of sentence that you would use if you're doing this problem on a free response question or something like that. And while I'm writing that out, I just want to say thank you for watching this video. If you thought it was helpful, then like it and subscribe to this channel. There are a ton of videos on different calculus topics, including all of the calculus topics that were on this worksheet. So you can see all of those in the differential equation unit. So thank you so much for watching, and I hope this was helpful. Remember that that worksheet is in the description below, and I will see you in more calculus videos in the future. Thank you.